So you guys are still, you can see my screen now?
Yep.
Okay, so this first little bit is on some properties, some logarithm properties, which lots of these, as you work through it, there's always a way to figure this out, but sometimes just a quick, if you remember the property, it saves you from having to work some of them out in all the way, right? So the first property we look at is if you've got the log of some base, in this case they said c, with a 1 after it, and that's equal to 0, well, your resulting answer, okay, is always going to equal 0, especially if you think about putting this in terms of an exponential, 3 to the power of 0 is always going to be 1, right? So if you've got log, so if it came out to log 5, 1, you know the resulting answer is going to be 0. Whatever your base, you're going to have any number down here. If it is a 1 right here, your resulting answer is always going to be 0. So that's all this first one is kind of telling you, is that you are looking at this and saying, hey, some base to the power of an exponent is going to equal 1. Well, that exponent has to equal 0. So that's that first property of logarithms. The next one is saying, well, if you've got that the log of some base, it could be whatever value you want. If it also has that same number, so if the same number shows up here and here, you know the resulting answer is going to be a 1. So let's think about this. If I put log 3 in here, it's going to equal 1. Well, convert it to an exponential. That's saying 3 to the power of 1 is going to equal 3. So if these two numbers are exactly the same, you're going to get a resulting answer of being 1. Okay, so same thing. I could say log 5, 5. We look at that and say, well, my brain is telling me 5 to what power is going to give me an answer of 5? Well, that power has to be 1. Okay, so again, you don't have to memorize these. You don't have to do anything with them really, but it is kind of like little shortcuts to it, right? If you recognize, oh, if this is like this, I know my resulting answer is going to be a 1. If I'm dealing with whatever base and it's got a 1 after it, I know my resulting answer for that logarithm is going to be a 0. Same thing in the next one. If you look at the next one now, it's saying log c to the power of x. Well, this is saying if you've got a number as a base and that same number shows up right next to it to a power of some number, then that your resulting logarithm, your answer to it, will actually be whatever that value is in your exponent. So in this case, if I had the log of 3 and it's 3 to the power of x, my resulting answer would be whatever that x is. Well, the reason for that is, think about it this way. If I plug this into exponential form, I would be saying my base of 3 to the power of x, that's this side, is equal to my resulting number, which is actually the same, 3 to the power of x. So it works out where our bases are identical, which would mean our x's are identical, right? So in this instance, if I said log 5 to the power of 2 is equal to something, think about it this way. If I wanted to know what this mystery number is, I'm going to go, oh, I need it 5 to the power of x, because I don't know what that number is yet, is equal to 5 to the power of 2. Well, if our bases are the same, look it only makes sense that our exponents have to be the same. So in this instance, a log 5 to the power 2, is simply whatever that exponent is. That becomes our resulting answer. And our last one, you've got c to the power of log cx is equal to whatever x is. So in this instance, what we're saying here is if I've got this value of a base of 3, but it's all to this power of log 3 of x, our resulting answer is going to be x. Well, this one takes us a little bit beyond what we've been kind of working with, so to speak. But convert this the other way this time. So let's think about this. This is in exponential form. Now what I want to do is put this into logarithmic form. So this is my base. So I would say log 3. Okay, my exponent is this log 3x up here. Well, that's going on the other side of my equation, because in exponential form, remember, or in my logarithmic form, should I say, that your exponent is always on the other side, right? So the base is here, my exponent is going over to the other side, which leaves me with my resulting answer as being an x there. So really what this shows me is that the log 3 of x is equal to the log 3 of x. So if I gave you log, oh, sorry, let's start this again. I said 5 log with a base of 5. No, I still did this wrong. Jeez, sorry. I'm going 5 to the power of log 5, and I say 2 there. Then my resulting answer for this will simply be whatever this value happens to be. That will be my resulting answer. So again, when we start to look at these last two in here, we're doing a lot of flip-flopping them back and forth between exponential and logarithmic forms. These aren't something I would expect you to memorize by any means, but like I said, they become a little bit of a shortcut of seeing things or recognizing things. Not mandatory. There's always ways. You look at what I've done is there are always ways to work it out. So if you've been given a logarithm, you can always, if you're stuck, convert it to an exponential and you're going to get your answer just like what you've been doing, right? So these are, like I said, these are kind of like little shortcut things that you might see that will pop up that you can get your answer quicker than having to do the exponential. But have no fear, if you forget the quick little roots, you still have ways to get there and get that same answer. Do you have questions?
I kind of lost connection in the between 1 and 2, but I just want to confirm if I'm correct. 1 works like since it's a 0, and if it were equal to 1, it would equal 0. And it's just being like the other way around?
Yeah, like the first one here, this is saying like c to the power of something has to give me 1, right? Because if I have a resulting answer that I have to get a 1 out of, well, the only way I can get a 1 is if my exponent is 0. So that's why this first one gives you, that's why the resulting answer of log, even if I take log 5 and I have a 1 here. The moment I have a 1 here, I know my exponent has to be 0.
Okay.
Okay.
That makes sense. I don't really get 2.
So 2 is basically saying I need to find whatever base I have to the power of some number has got to give me the same value that I started with. Well, the only way I can put a power into my whatever my base is and get the same number is if I put a 1 there, right? Like, because I'd go 5 to the power of 1. Oh, that's going to give me the 5 I need, right? 10 to the power of 1. Oh, that's going to give me the 10 I need. So if these two values are identical, that means that you're looking at an exponent. In order for these to be identical, I have to have an exponent of 1 only.
Okay.
Okay?
Yeah, okay, I get it.
Okay. So now what I want to do is let's look at some of these in terms of just finding the value of x, finding the missing number that shows up, right? And it's not always now going to show up in your as your exponent that you're trying to find. It might be your base. It might be your resulting number that you need to find. But the thing is, as you work through these, you're still going to set them up as exponential form, okay? So whenever you get a question like this, you could set these up as an exponential form. You can, like, that's where my brain goes. If you're trying to evaluate something or figure something out, you got to get it out of logarithmic form and into exponential form. So in this case, when I look at this, if I'm going to convert it to exponential, I've got a 4 as my base. My exponent is -2, and it's got to equal x. Well, holy, we're almost there, right? This is a scenario that we've got our base and our exponent. Now we just have to figure out what that is. So in this instance, I treat this as, oh, that's like saying over 1, right? I had a negative exponent here, so I can rewrite that as 1 over 4x squared, or 4 to the power of 2, which then 4 squared, well, I know 4 squared. 4 squared is 16. So this is the same as saying 1 over 16 is equal to x. And that represents my number. How does that one feel?
Yeah, I get it. I just kind of got confused at first. The exponent is, no matter what, it's connected to its base number. Like,
Yes.
yeah, I got a bit confused, and I thought maybe you could turn the -2 into a half by putting a 1 over it. But that.
Oh, no. No, we have to move it down to the denominator instead. Yeah.
Just got a little confused.
Okay, no worries. Okay, so look at the next one. So if the next one is log 16x is equal to -1/4, so rewrite it as a exponential form. So I've got 16, my exponent is -1/4 is equal to x. So same thing, I got that negative exponent. I'm going to treat that over 1 again. So I'm going to bump this down to the denominator. Problem is with this one, what does that quarter mean? Having an exponent of a quarter like that, what does that mean? So if I have a base to a power of a half, that would mean that I would be looking for my square root, right? So if I have a base where I'm looking at a quarter, that means I'm looking at finding the 4th root of whatever that base is. So in this instance, this is the 4th root of 16 equals x. So now I have to figure out what is the 4th root of 16? What does that equal? On that, you should be able to do in a calculator, right? Are you getting x is equal to 1/2? Because this here, the 4th root of 16 equals 2. And I still have it over 1, right? So, or under 1. So that should be your resulting answer, is 1/2. Now the next one, I've got a base this time that happens to be x. I've got a power of 2/3, and that equals 9. So these ones are fun. So basically what this means is I've got this 2/3. That's x to the power of 2/3. I'm going to rewrite it with a root in it, right? Because the moment I have a fractional exponent like this, I'm going to have a root. So this is because my 3 is in the denominator. That means I've got a cube root, and my x is being squared right now. So right now, and then that's equaling 9. Now, ultimately, I need to get this to a resulting answer where I'm just saying x equals something, not x squared, not cube root of x. I need it just to be a plain single x. So you're going to work on the outer first and work your way into the x. So my first thing I need to eliminate is I've got this cube root. What's the opposite of cube rooting something? I hope you're saying, hey, I have to cube it. So in order to take the opposite of a cube root, I have to actually cube it. But if I'm going to cube the one side, I better cube the other side, okay? So by cubing a cube root, I am really leaving myself with an x squared, okay? So that's all I'm doing is I'm basically canceling out that cube root piece to it. On the other side, I've got 9 cubed. I better figure out what that is. 9 cubed gives me 729. So now I've got x squared is equal to 729. So again, I needed to get to an x, not as an x squared. So now the opposite of squaring something is to take the cube root, or take the square root, sorry, of both sides. So if I take the square root of 729, I'm going to find out that x equals 27. So that one is a little bit trickier because of the fractional exponent and in introducing this cube root and the square in here, and always thinking what's the opposite of what's happening to the question to kind of work your way through it. Do you have questions on that one? Not bad?
Just kind of where the fraction turns into the squared, the radical, but that makes sense.
So the number the numbers that's in your denominator is one that's going to tell you your root, and the squared is just, it's an exponent, it's a power, right? So it's going to show up with whatever that variable happens to be. Yeah, that'll be the biggest thing, right? Just to kind of keep that straight, because a common mistake here is to get the 2 and the 3 flip-flopped, right? So I always think my number in the top still acts like a power, right? It is still, I'm not dividing by anything. It is a full-on whole number as is. The one in the denominator is, it's a fraction. It's a piece of it, right? So that means that it must be a piece of that base number that you're working with. Okay, so let's look at D. D says log 5x is equal to -3. So my base is 5. My exponent is -3, and that equals x. You guys, we're doing a lot of these with the negative exponent, but these are good. This gives you a good sense of what to do and gets you comfortable with dealing with that negative exponent. Again, got to make the exponent positive in order for us to evaluate that. So I'm going to go 1 over 5 to the power of 3. And then when I figure that out, 5 to the power of 3 is simply 125. So that one feels like a piece of cake after we just did C. And then E, I've got log x 36 is equal to 2. Same thing, convert to exponential. So x is my base, 2 is my exponent, and that equals 36. And then same thing, just like what we did in the one above up here. I've got x squared is equal to 36. So now my options are going to be where I have to take the square root of both sides. which is going to leave me with x is equal to 6. And that will be my answer. And think about it, if I put a 6 back in here for x, I'm going 6 to the power of 2. Does that give me 36? Sure does, right? So you can always go back and have a look to see if it actually makes sense what you're working with. Now, example 3 looks into estimating, okay? So estimation isn't about actually finding an exact value. It just wants to be, are you in the ballpark, right? Is it, what would be kind of a logical answer to this? So when you go to estimate, just like you look at determining and evaluating something, you want to look at this in terms of, let's put it in an exponential form that we can work with. So again, this is really saying 2 to some power is got to equal 14. Now looking at that, I hope when you see that, you're recognizing, oh yeah, there is no 2 to a whole number that will actually give me the answer of 14. So what you want to do in these ones now is to kind of find, think about your common powers of 2, and think about finding one that gives you an answer just above the 14 and gives you one just below the 14, because it kind of gets us into the right range of where we're supposed to be, right? So in this case, I look at this and go, oh, well, I'm going to have 2 to the power of 3. That would give me 8. I know 2 to the power of 4 gives me 16. So right there, I know I'm going to be between 3 and 4. If I look at 14, I look at that, that's closer to 16. It's more than halfway to 16 from 8, right? So then I look at this and go, well, I've got to be 2 to the power of 3.5. I think I'm going to have to be a little bit higher than 3.5, right? This is where the guesstimation kind of comes into play, but you're being kind of logical about it too in the grand scheme of things. So if you put, so maybe it's not 3.5, maybe we go 2 to the power of 3.6, and we try that in our calculator and go 2 to the power of 3.6, and I'm getting 12. Like I'm still low on that one. So I know I can't be 3 to the power of 3.6. So maybe I'm closer to 2 to the power of 3.8. So if I go 2 to the power of 3.8, I get 13.9. That's getting pretty darn close. That's a pretty good estimate of what I think this logarithm should be. So in this instance, I might say x is approximately maybe 3.8, might be 3.82, 3.81, but it's an estimate, right? So that's why I use these little squiggly equal sign, just to show that it's not exactly 3.8, it's about 3.8, right? It's an approximation. Does that make sense? Okay, so if we look at the next one and we say log 3 of 30, same thing. This is really saying 3 to the power of something has got to equal 30. But we want to know what that approximation is or what that estimate is. So again, let's think of something just below it, think of something just above it, and then that's going to give us some guidance in trying to get us in the right ballpark at least. So we could look at this and go, oh, 3 to the power of 3 gives me 27. So that's just below it. That's easy. So I'm guessing 3 to the power of 4. Well, 3 to the power of 4 is going to give me 81. That's really high. So in looking at my numbers, 27 and 81, and thinking about where I need to be, I'm going to be closer to the 27 than I am to the 81. So I'm guessing for an estimation, I might even pick 3 to the power of 3.8 Maybe it's 2. Maybe that's too high. Let's try it out. 3 to the power of 3.2 gives me 33.6. So that is, we went too high on that one. So let's try 3 to the power of 3.1. And there I'm sitting in at 30.13. So to me, because it's an estimation again, I'm not looking for exact, I'm going to say that x is roughly 3.1 as my exponent. That's going to get me pretty close to that 30 as a resulting answer. So when you see questions or you're working through questions and you're asked to estimate, this is what you're doing. You're picking a low and you're picking a high around the value that you're trying to find, right? And then from there, you're going to kind of then start to guesstimate. You're going to use, right? You can use your calculator to find out those little pieces. I don't want you to go and plug in the value right into your calculator, right? Or figure it out. In this case, you'd be looking at finding a cube root, and you don't, in this one, you would be finding a cube root and you don't need to find it exactly. I just want an estimate. If I saw an exact answer, I'd probably mark it wrong because you didn't follow suit in understanding what estimation would look like, right? So how does that feel?
I get it.
Okay. And the other equations? Those okay?
Yeah, I might need to look them over again though. I get the basics of it.
Yeah. The biggest thing here, we've been so used to, and you've been so used to just solving for x, which happens to be your exponent all the time. These ones just look at it from a different standpoint, right? So where you're trying to find what the base is or trying to find out what your other number is. So it's not always just looking for just that exponent, the missing exponent, right? So yeah. It's creating that flexibility, right? Of understanding that you can write things as an exponent or exponential form, and then solving for whatever missing piece that you've got. Winnie, how are you making out?
It's good. I get it.
Okay. Okay, so then what I want you guys to do now you can go ahead and finish off assignment 1. So you've got, basically, I think it's just question number 6 in that first assignment, and finish off any other ones along the way that you haven't been working on. And then on, it's going to be a while, hey? On Tuesday, we'll meet back then and we will work on transformations.
All right.
That sound like a plan?
Yeah. When are you planning to do the test or review?
For this one, I would assume it's going to be next week.
Okay.
Right, because we'll do transformations. This isn't a long unit either, so we'll do transformations. We might plan to write that test by next Friday if it works out that way.
Okay.
Does that work?
Yep.
Yeah, because I don't think we want to extend it too long. The transformations piece, once I show you the setup of it, your A, B, H, and K, all of that still follows suit of what we've been doing. It's just the initial piece that we're going to play around with on Tuesday will be just slightly different, but at the same time, not completely out of whack, right? Like it's not something brand new. It's just something to be aware of when we're looking at these equations. It's just basically looking at X and Y being in a different spot. That's all.
Okay.
Okay.
Yep.
So not bad, not bad. All right. Well, I will let you guys go then if you guys have no further questions, and we will, like, you guys text me too, right? Like anywhere along the line, if you guys are having difficulty with a question, just throw me a text and I'm more than happy to help you between now and next Tuesday. And yeah, we'll meet Tuesday at 1 o'clock, kind of our usual time, and we'll continue on.
Okay. Thank you.
Thank you.
You're welcome. See you.
Bye.
Bye.